Okay, let's go to chapter 6, which is work and kinetic energy. Let's just start defining these two concepts. We have work is energy transferred to or from a body by the application of a force. Also, we can say that work is the product of the displacement and the component of the force in the direction of the displacement. Also, energy, we can define it as anything that can be converted into work, anything that does work. Also, we can define it as stored work. Okay, let's start with a definition of work. This one, the second one, it says is the product of the displacement and the component of the force parallel to the displacement. Right, in this case, we're dealing with two vectors, force and the displacement. So we're dealing with a product of two vectors. In this case, we have the application of the dot product. Let's see. By definition, we have that if this is an object, right, this is the surface, later the object is at this position due to the application of this force, correct? Then imagine this is the displacement from here to here, displacement S. According to this definition, work, the symbol for work is W, right? Work is equals to this product, the product of the force, correct, times the displacement. Actually, it's gonna be what? The product of the displacement and the component of the force in the direction of displacement. In this case, what is the component? Well, in this case, these two are parallel. So it's gonna be force times S, correct? But it's a product. Okay, it's gonna be the dot product of these two vectors, correct? Perfect. Now, what happens if the force now is not parallel, like in this case, right? If the force is not parallel, like in this case, right, we have an angle, it's the same force, right, the same direction. In this case, the force is constant. For this particular case, again, the force is constant, so it means what? We have always the same magnitude and the same direction. Okay, imagine that we have this situation again. So what should be the work for this case? Work is gonna be equals to the component of the force in the direction of the displacement. This is the theta. So the component is gonna be F cosine theta times S. Correct? And this is equals again F S cosine theta. And one more time, this is equals to the dot product of these two vectors. So we have then the definition of work. What is the product of the force and the displacement? Is the dot product. Means that we are dealing with the component of the force in the direction of the displacement. Now, what happens if we are dealing with this situation, right? And in this case, the force is opposite to the displacement, correct? All the time, the force is constant. Perfect. Now, in this case, we applied the definition of work, which is this one, so it's equals to Fs cosine theta. But what is the angle between the displacement, right, and work? This is displacement in this direction, and this is force. So the angle is 180 degrees. So cosine 180 degrees is -1. So this is equals to negative F, right, times the displacement, negative. And one of the examples for this is when we have friction, right? Where we have an object that's sliding, right? It moves from one position to another position, but friction is opposite to motion in general, correct? So, and this is the case for friction, it's gonna be negative. Also, we have other cases where the work is negative. By convention, we use this if if we are doing work on the system, right? The work is positive. If the system is doing work, right, the work is negative. Imagine this is the system, right? We have work right into the system, so work is positive. If work, let's say, is coming out or is done by the system, correct? Work is negative. That's the convention that we use. We can change the convention, of course, but so far let's use this convention also to indicate the direction of work. Correct? Perfect. Also, it's a new quantity. Remember, every time we have a quantity, like a force, remember in physics we have two groups of quantities, scalars and vectors. Correct? If we multiply these quantities, we create new quantities. Right? Like in this case, force times displacement, we have a quantity times another quantity, we create a new quantity, and we define that quantity as work. So this quantity, this new quantity also has units, right? Perfect. What should be the units of work? The units of work are called joules, right? Unit, right? Joule. Perfect. So 1 joule is equals to 1 Newton times meters, times 1 meter. Correct? And this is the definition. 1 joule is the work done in moving, right, an object, right, a distance of 1 meter when we apply a force of 1 Newton. Imagine from here to here is 1 meter. We have this object right here. When we move this object from here to here by the application of 1 joule or 1 Newton, so the work done is equals to 1 joule. Okay, great. Now, let's go to energy. We already defined energy, correct? Anything that can be converted into work or stored work. Perfect. Now, in this case, when we're dealing with kinetic energy or energy, right, we have in mechanics two types of energy. Mechanical energy. Energy, correct? We have two types. We have kinetic energy, kinetic, right? Energy, the symbol is K, and this is due to motion, right? Due to motion. And also we have a potential energy, right? Potential energy. For potential, the symbol is U, right? Potential energy, we have two types. We have elastic and gravitational. All right, gravitational and elastic potential energy, and this is due to position. Correct? Perfect. And the same thing as before. As for work, the unit is joule. Unit of energy, right, is joule. The same thing as for work. Correct? Now, let's try to find formulas that represent energy. Okay, let's do it. Let's start with work. One more time, imagine that we have this particular case where we have an object with some mass, correct? And we apply a force in the direction of the displacement. And from here to here, we have the displacement, correct? The force, one more time, is constant. What should be the work in this case? Well, let's do it by definition. Right, work is the dot product of these two vectors. And this is equals to Fs, right, cosine theta. What is the angle between these two vectors when these are parallel? 0. Cosine 0 is 1. so it's equals to F times S. Okay, now because the force is constant, right, so the acceleration is constant. And every time we have constant acceleration, remember from previous chapters, we can use kinematic equations, correct? Now from kinematics, let's try to find an equation that involves the acceleration, and in this case, the displacement. Let's do it. So from kinematic equations, we have one of them, which is final velocity squared is equals to initial velocity square, right, plus twice the acceleration times the displacement, correct? Now look right here, also from here, what should be force according to Newton's second law? Force is equals to mass times acceleration, in this case times s. Look, we have acceleration times the displacement that appears right here. Let's start from here, right, for AS. Okay, so acceleration times displacement is equals to final square minus initial square divided by 2, correct? Let's apply this quantity right here, and what do we have? Well, in this case, we have, let me see, we need more room. Perfect, we need more room right here. We have that work is equals to mass times acceleration times s, and this is equal displacement. This equals mass times final velocity square minus initial square divided by 2. Correct? Great. Now let's do this multiplication. What do we have? 1/2 mv final square minus 1/2 mv initial square. The same thing as before, we have a quantity multiplied by another quantity. We create a new quantity and we have to define it. We have to call it, name it. Okay, and we define this as the kinetic energy. So kinetic energy is a definition, okay? Kinetic energy is equals to 1/2 mv squared. When we apply that definition right here, what do we have? We have that this is equals to kinetic energy at the end minus kinetic energy at the beginning. Now what is this? The final quantity minus the initial quantity is just that change, right? So this is equals to the change in the kinetic energy. So work, actually this is the net work. Remember, because we're dealing with this force. When we're dealing with forces, like in this case, this force is the net force in general, right? This is the net force. Also, we can say, right, that work, the net work is equals to what? It's equals to F1, right, times F1 plus F2, correct, times the dot product F2, right, and so on. Remember, this is the net work. It's the sum of the work done by all the forces. If we represent this by the net force, one more time in this equation, it's gonna be the net work. Perfect, yes. So net work, oops, net work is equals to then the change in the kinetic energy. This is called the work energy theorem too. Okay, so this work equals to the change in the kinetic energy is called the work energy theorem. Remember, these are ideal cases. We have no friction, right? Nothing is involved, only, right, the pure physics, correct? Interactions in this case, because we're dealing with forces. When we're dealing with forces, we're dealing with interaction, remember? Great. So it's gonna be work energy theorem, correct? So as you can see, we have energy, correct? And this is work. If work is in joules, energy must be in joules too. So they have the same unit, right? Perfect. Now, we mentioned before that for this case, so far work force is constant. Okay, force is constant. we can plot, right, this product, correct? This is the distance, right, and this is the force applied. When force is constant, well, we create this graph. How we can find work? Remember, work is what? Work is the product of these two quantities. But the product of these two quantities in this graph give us the area, right? So this is the area under the curve. So this is work. Another way then to find work is finding the area under the curve. Correct? Perfect. This is the case when force is constant. What happens when force is not constant? Well, one way how we can find then work is using the graph. If we have a graph, correct, like in this case, and this is again force, and this is displacement. We're looking for the work done from this position to this position, correct? Well, we just find the area under the curve, and that's gonna be the work done, right? Work area under the curve equals to area, right, under, right, the curve. Perfect. So we have a one case that is happening in nature, right, that give us force is changing, right? For example, when we have the spring, let's go to the spring, correct? Let's go to the spring. When we have a spring, we know that if this is the spring, correct, and this is in equilibrium, mean x equals to 0. What happens when we apply a force? Well, when we apply a force, right, the length, right, of this is a mass, right, mass of the spring increases. So in this case, we can say that force is proportional to x, right? How much is stretched this spring. The same thing happens when we compress it. The same, it has the same meaning, right? The same behavior. Correct. How do we eliminate this symbol? Well, in this case, we have force is equals to k. Remember how to use a constant times the displacement. Correct. In this case, k is called the spring constant. Spring constant, and that depends on the spring, right? Perfect. Now this is again, we call this the applied force. Applied force. The applied force. What should be the force done by the spring, right? The force done by the spring is equals to, well, in this case we use action-reaction law, right? Newton's third law, right? If this is the action, what should be the reaction? Negative kx, right? And that's the force done by the spring. Again, this negative sign indicates that the force is toward the equilibrium position. This is also called a restoring force, right? Restoring force. Like in this case, if we apply a force in this direction, right? This is the force done by the spring, goes opposite, goes to the equilibrium position. If you compress, you apply a force, right, to compress the spring, so the force done by the spring is opposite, right? It's opposite, always toward the equilibrium position. That's the meaning for this negative sign right here. Right, perfect. Now, one more time, if we have this curve, right? This is force and this is s. What should be the work? The work in this case. Well, in this case, remember, we are looking for the area. But one way how we can find area is using integrals, right? So actually, gonna be the integral of force, right? That ds. Correct. The same thing as in calculus, right? When we are dealing with areas, but we use the integral. The same thing happens right here. Correct? We can use vector because it's dot product vector vector. Got it? Perfect. From initial position to final position, let's say. Correct? Also, we can use x. Usually we use x instead of s, right? Like in this x, right? We are dealing with x in this case, so we can use also work equals to the dot product of force, right? The x. Correct? From initial position, right, to final position. When we're dealing in one direction, x direction, for example. Perfect. Now let's go to the spring. As we can see, the force is not constant, it's proportional to x. Now, what should be the graph for this function for the spring? Let's do it one more time. Let's write this force done by the spring near kx. Perfect. So we can calculate then the work done by the spring in two ways, using the graphs and using also work, right? In this case, intervals. Let's do it. So for example, imagine that this is the applied force, correct? This is applied force, and this is, let's say, x, displacement. So according to this is force is equals to kx. Kx, remember, this is similar to have y equals to mx. So this is k is gonna be the slope, correct? They have the slope. This is linear equation, right? It's gonna be like that. Perfect. And then what do we have? Well, what should be the work done? Okay, work. Work is equals to the area under the curve. What is the area? Okay, let's find the area, which is gonna be this one, this area. Okay, which function is this one? That's applied force, right? Equals to kx. Correct. How we can find the area? Area is equals to force times x. Correct. But what is force? Force is equals to what? Okay, well, we're looking for the area, right? The area is force times times the distance or height. What should be the height in this case, right? In this case, we have this equals to it's divided by 2, correct? So it's equals to, again, this is the equation right here. Also, right at this position, right, we have the same quantity. Perfect. Okay, it's gonna be the equals to kx, which is the force done by the spring times x divided by 2. This equals to kx squared divided by 2. Correct? Also, as before, we have a quantity, right? This is a quantity because also has a unit, right? It's a constant too, correct? Times x squared. This create a new quantity, correct? This is called potential energy, or is defined as potential energy, elastic potential energy. So elastic potential energy, correct? Let's define it as US, right? So US is defined, remember it's our definition, right here. Is defined for the spring kx squared divided by 2, right? So we have another quantity, right? Elastic potential energy is equals to, or is defined as kx squared divided by 2. Correct. Perfect. Now let's use let's do this in the world using calculus, using the integers. Okay, let's do it. So work then is equals to, from here, This is 0 and this is x right here. So work is equals to the integral from 0 to some position x of this product, correct? Component in direction dx. Okay, let's do it. So it's equals to the integral from 0 to, or we can take actually from any position right here, any two positions in general. Let's say initial position, final position, initial and final position, right, of this product. Let's do it. So it's equals to the integral, initial position, final position. What should be this force gonna be kx, correct, dx. Okay, what is that integral then? Work is equals to kx squared divided by 2 from initial position to final position. For final, we can just make it like that, final. And then when we substitute the values, this is equals to, remember this is a force done by the applied force, right? The applied force. This is the work done by the applied force, right? The applied force. This is equals to what? It's equals to k, the spring constant, final position square minus k, spring constant x initial squared divided by 2. Correct? But what is this? If we define one more time elastic potential energy in this way, so what do we have? This is final, right, elastic potential energy minus initial elastic potential energy. Okay, elastic potential energy final, elastic potential energy initial. But what is this? That's the change again, right? So it's equals to the change in the elastic potential energy. This is the work done by the applied force. What should be the work done by the spring? Using action reaction law. It's gonna be negative, correct? So then the work done by the spring is equal to negative the change in the elastic potential energy. And you can see, right, they have the same form, right? Work using the network is changing kinetic, and the work done by the spring is negative change in elastic potential energy. Correct? Okay, perfect. Also, we have to explain this later. When we have something like this, right? When we have the work done, is equals to negative change in the potential energy. Remember, so far we have two in mechanics. We have gravitational potential energy and elastic potential energy, right? When work is negative, the change in the potential energy, right, is because this force, the force done by the spring and by gravity, are conservative forces. So these are special forces. Later, we have to explain, right, or define a conservative force in the next chapter. Correct? Perfect. Great. Now let's go to the last topic in this chapter. The last topic is gonna be power. Yes, let's go to power. Power. Power is defined as the rate at which work is done, right? Rate at which work is done. The symbol for power is P, right? Is equals to what? Work divided by, okay, time. Correct. Also, work equals to what? To work equals to, also equals to what? Change in kinetic energy, correct? So we can say also is equals to change in kinetic energy, correct, divided by the time. So we can use this equation. Sometimes we use this quantity, right? Energy divided by time. Actually gonna be the change energy divided by time. The same idea, correct? Perfect. But let's go to this definition, right? work divided by the time. Also, look, we have a quantity divided by another quantity. We create a new quantity, we have to define it. We define it as power. Definition, power, perfect. So we have power is defined as work divided by the time. Great. Now let's see how far we can get, right? Or we can go from this equation. Now let's work with work, right? Work is just what? Work is the dot product, right, of force and displacement, and then divided by time. Correct? But we know that this quantity is given, correct? This displacement divided by time is velocity, remember? So it's equals to the dot product of force times the velocity. Correct? How we can represent power. So power is also equals to this dot product force times the velocity. Correct? And we apply this one mainly when velocity is constant. Got it? Also we can okay, let's go to the unit, because it's a new quantity. The units of power are or is what? Unit watts. Correct? Watt. The units of power. Correct? Also, we can use so 1 watt is equals to 1 joule per second. Correct? Great. So again, this is power, and in this chapter we have these topics: work, kinetic energy, potential energy, and power. So with this we finish this very short chapter, and see you in the next chapter. Thank you.